Dear students, today let us see the derivation of Gibbs phase rule. This phase rule is the relation between the number of components and number of phases and the number of degrees of freedom in a system. The degrees of freedom is defined as the total number of independent variables such as temperature, pressure, and concentration or composition which must be specified in order to define the system completely. In other words, the degrees of freedom can be calculated by the total number of variables in the system minus the number of relations that imposes restriction to the system. That means the total number of variables, that is temperature, pressure and composition, all the variables are not independent. The degrees of freedom says the variable must be independent. But the total number of variables that we have here are all of them are not independent, and therefore we must subtract the number of relations that impose restrictions to the independence. Okay, let us derive. With this note, we shall derive the Gibbs phase rule. For the derivation, let us consider a heterogeneous system which contains C number of components, and that is explained here. Let us see, these are the number of components here, that is component 1, component 2, component 3, component 4, etc. until component C. And each component exists in different phases, and that is given here. For example, the component exists in alpha phase, and it may exist in beta phase, it may exist in gamma phase, etc., up to p number of phases. Similarly, a component 2 may exist in alpha phase, beta phase, gamma phase, up to p phase. Similarly, okay, and this is the system we consider for the derivation of Gibbs phase rule. Okay, for this system we are going to calculate the total number of variables and the number of restrictions, a number of relations that impose restriction to the system. And if we calculate this, we can calculate the degrees of freedom, and finally we can derive the relation from this. And therefore, first let us calculate the total number of variables for this system. As we have already seen, the temperature is one variable, and pressure is another variable, and the composition is another variable. There are C number of components, and that exist in P number of phases, and therefore the total composition will be C multiplied by P, and therefore total number of variables will be Cp, C multiplied by P, Cp plus 2, temperature 1 and pressure 1. These are the total number of variables, Cp plus 2. Kindly remember this, and we will use this while deriving. Our next aim is to calculate the number of relations that impose restrictions. Now we have already calculated there are total number of variables that are Cp. The total number of variables are Cp plus 2. Not all these variables, as I have already told you, not all these variables are independent. and we have to subtract the relations that restrict the independence. Okay, as we have already said, not all the variables are independent, and therefore we are going to calculate the number of relations that impose restriction to the system. To calculate that, the restrictions are imposed by several factors. Number one, by the each component. When I mean each component, actually the mole fraction of the component actually imposing restrictions. Okay, the mole fraction of the component. So the sum of mole fraction for each component is equal to unity, that is 1. That means this is xi alpha. If you take a one phase, alpha phase, the total number of alpha phases, okay, component 1, component 2, component 3, etc., that will be equal to 1. Similarly, for beta phase, the mole fraction, the sum of mole fractions of component 1, component 2, component 3, etc., of a beta phase, that will be equal to 1. That is the mean. Similarly, for each phase, the mole fraction will be equal to 1. And therefore, the total restrictions by each phase will be equal to, there are total p number of phases, and each phase mole fraction is 1, and therefore the total restrictions will be equal to p. Since there are p phases, one phase gives one restriction, and therefore p number of phases will give p number of restrictions. The second restriction is imposed by chemical potential. The chemical, to understand chemical potential, the chemical potential of each phase of a component must be same. For a component, the chemical potential of each phase. For example, the chemical potential of first component alpha phase and that of the beta phase must be equal. That is what the chemical potential of a system says. Similarly, the first component gamma phase, that will be also equal. Similarly, for the second component alpha phase chemical potential and the beta phase chemical potential are equal, and that is equal to the gamma phase. Okay, there may be similar relations you can write, and totally there will be p minus 1 number of such relations for each component. Okay, if you write in equation, I will write in a separate paper, I will explain that in a separate paper. If you have two, for example, if you have two systems A and B that are in equilibrium, that means there are two components but the relation is 1. Okay, if there is a third component A, B, C, there are three components but the relation is two relations. That is, there is a relation between A and B, that is relation 1. There is a relation between B and C, that is relation 2. And therefore, to calculate the number of relation, you must minus 1 from the total number of phases. And therefore, there will be P minus 1. That's why total number of phases are P, but the number of relations will be P minus 1. P minus 1 number of such relations for each component. Okay. There are C number of components. For one component, it is P minus 1. But there are C number of components, and therefore the total relation will be C multiplied by P minus 1. These are the restriction. The third restriction is imposed by chemical affinity. The chemical, as far as chemical affinity is concerned, at equilibrium, the affinity must be zero, and therefore, and that is AFI for component 1, for component 2, for component 3, etc. up to R dash, and that is equal to 0. And therefore, the total restricting relations is the total restricting relations we can calculate, and this is the restriction by mole fraction, and this is restriction by chemical potential, and this is the restriction by chemical affinity. Okay, we have calculated total restrictions. Earlier we have calculated the total variables. Now we can calculate the degrees of freedom F, that we have already know. The degrees of freedom F is equal to total number of variable minus number of restricting relations. We know already that the total number of variable that we have already derived is Cp plus 2, and the number of restrictions are P. Okay, P plus I have multiplied this C into P Cp, I have multiplied C minus 1 C. Okay, plus this R dash. Upon solving this equation, Cp plus 2 minus P minus Cp minus multiplied by minus, that is plus C, plus R dash, which is 0, that we have already seen. And solving this equation, we get Cp and Cp cancel out, plus Cp minus Cp, and other things are plus C here, minus P here, plus 2 here, and this is 0, and this is F is equal to C minus P plus 2, and this is the phase rule. Thank you. We shall meet in another video. Thank you.